I don't have a microphone, but can everyone hear me? Okay. So first, a personal admission. I watched a lot of Star Trek as a kid. The original episode. Thank you. One thing that struck me as a kid watching those episodes is they always referred to a time. So they had this civilization where they had overcome basic issues of survival and human justice, and they had this great civilization. Then they had these starships going off to explore other worlds. And they referred to a time of a technological adolescence that they barely got through. And I realized that that time was my lifetime. And so I'm very concerned about the future. We're putting enormous strains on our environment. And it's like, how do we get through? And things like this, getting innovators together to do, combining all kinds of insights. My dream was to see that come to fruition. So the first thing, I'm going to try to go quickly. It's a lot to absorb, but in the early days, throughout human history, when we've discovered new ways of harnessing nature, it's led to radical leaps in our capability as humans. These are some big examples: fire, agriculture, tool making, the Industrial Revolution, nuclear energy, electronics. And in each of these, there was a first, say, revolution in our use of these resources. So take fire as an example. There was a phenomenon we saw, it was mysterious. We started using it, but we didn't know how to create it initially, and we didn't know how to manipulate it in a detailed way. So there was a second revolution, say when we figured out how to make the fire hotter by adding a bellows and oxygen, and then we could do metallurgy. Or in the case of agriculture, where I could start cross-pollinating plants rather than just planting for food, and I could create new species with desired characteristics. Quantum computing is this kind of thing. It's not the next generation supercomputer. It's a paradigm shift. So we have this very, very complex civilization we've built. And the systems, whether they're energy systems, transportation systems, financial systems, have grown beyond our understanding. They transcend human understandings. When people talk about financial markets, I hear this on the TV all the time, things crashing. We don't understand why. We can't model systems with an enormous number of interacting variables sufficiently with the greatest resources we managed to create so far. So what's next? And I think it's going to take the collaboration of innovators from all over the world working on all these diverse technologies you're going to be hearing about at this workshop. But I'm going to talk about a possible unimaginably powerful resource that we're developing now. Next. Okay, so the first thing is that human beings aren't smart enough to figure this out on our own. Our brain aren't designed to solve multivariable problems at those kinds of scales. So the first thing is we now are augmenting our human intelligence. What I call networked brains, an amazing development with the internet. Say, we have researchers, scientists from all over the world that can communicate at rates never before possible. There's this combinatorial explosion of ideas giving rise to a Moore's law-like effect in terms of the rate of development of new technologies and ideas. We've built massive classical computing. That's a Google computing center, crunching amazing amounts of data. And of course, we're creating enormous amounts of data. Genetic data is an example. Right now, we're not necessarily able to extract meaningful insights from all that data on time scales that matter. And in addition to all of that, now we're making machines that can learn. So that represents an artificial neural net. We put together elements that are rather like neurons. They have this complex interconnectivity. And when we want to do something like have a computer learn to understand natural language, or to be able to look for patterns in complex data, or do image recognition, we build something like neural nets in a human brain. And since we don't know how to explicitly program that thing to look for those patterns, it learns. It goes through a recursive cycle where you get input, output. It adjusts its own neural structure until it becomes the kind of thing that can understand natural language. But the interesting thing is, with all of that, and these are awesome resources, they may not be enough to solve the scale of problems that we face as a civilization. And I'll tell you why. So there's a discipline that's called complexity theory, in which people characterize the resources it takes to solve problems. And the way they characterize how hard a problem is how the resources to solve a problem grow as the size of the problem grows. And we have a theory of computing that underlies all of our computation to date. And when you can see two different scaling curves. One scaling is called polynomial. It goes like a square or a cube, wherein as this problem gets bigger, the resources required, say, go up as the square of the size of the problem. Those are called tractable. And these are the kind of problems with current resources that use the kind of physics that we have available in those machines that we could solve as a civilization if we threw a lot of resources at. There's another class of problems where the resources required blow up exponentially as the problems get bigger. The interesting thing is that this characterizes a lot of the problems we face as a civilization today. For instance, optimizing complex systems. So let's say you wanted to, a mundane example, FedEx wants to figure out how to route all its packages to minimize fuel consumption. That's beyond our grandest supercomputers to find the optimal solution. In pattern recognition systems, trying to train those networks in an optimal way is a very challenging computational project, even for the grand data centers at Google. Simulation of quantum systems, that's all of chemistry and biology. You've heard people talk about these enormously complex cell biology, molecular biology. Our grandest supercomputers can't simulate the behavior of the caffeine in your coffee, let alone more complex molecules. So there are problems whose complexity scales so dramatically that we've thought these will forever remain beyond what human beings can calculate, and I think it's actually important to be able to solve those problems as our civilization is replete with them. So at the beginning of the 20th century, there was a radical change in thinking about the nature of physical reality that was called quantum theory. Quantum theory explains everything that can be explained, say other than gravity, which is general relativity. It explained the structure of matter and radiation, which is just about everything that you experience. And there was what I call the first quantum revolution. We understood why the sun shined with fusion reactions, which might be a source of sustainable energy going forward. All of chemistry, molecular biology, those understandings are made possible by this theory. It led to the semiconductor revolution, the transistor, and everything that came with that. Lasers, telecommunication, nuclear reactions, nanotech. All of that was enabled by the understandings that came about at the beginning of the 20th century, quantum theory. But the interesting thing about quantum theory is that people have been using it for the last 100 years. It's never been violated in any experiment ever done, and yet it says the ideas that underlie quantum theory that give us these amazing understandings are some of the strangest ideas humans have ever encountered. And there was almost incredulity about whether it could possibly be true, because the other thing it says about the world is that there's this strange parallelism in the world, that physical objects can occupy several different states simultaneously. This is the famous Schrodinger's cat that's alive and dead simultaneously. So particles at the microscopic level, people would see a single electron in many places simultaneously, living out many possibilities simultaneously. And one question was, why don't we see that at macroscopic scales if we're built out of those things? So for a long time, I think quantum, a lot of people working in the sciences had the shut up and calculate sort of philosophy. It's like, could the world really be that world? Are there these parallel realities playing out all these multitude of possibilities? Well, it gives us the right answers. There were a lot of ad hoc features added to quantum theory to kind of do away with that. And I'm going to tell you about some of these features. that for the first time in human history in the last couple decades, we're able to manipulate at will. And this allows for an astounding possibility. So the first of these I've already mentioned, superposition. It's called quantum superposition, where a single entity, this is an object, say, traveling from point A to point B. It doesn't take a single trajectory like you're used to. It actually explores all possible trajectories. That's a very small subset of that. But imagine if that was you living out many possible histories simultaneously. So I'll tell you quantum computing in 5 seconds. Imagine you had a math problem. Well, I'll make it easier. Let's say you go to the Library of Congress. There's 50 million books. In one of them, I secretly put an X on one of the pages. I tell you to go into that library. I want you to find the X. You have 5 minutes. You say, well, okay, it's going to take me many lifetimes to go through those books sequentially. I'm not even going to take that problem. But if somehow I could put you in this magical quantum superposition in which you were in 50 million parallel realities, and in each one you try a different book. Now, the other important feature is that you have to be able to collaborate with all your other selves. And these aren't clones of yourself. The same physical matter is somehow playing out all these different roles. Talking to your other selves we call coherent evolution. You're kind of coherent to your other selves, and you can share information. Well, now you find the book very quickly. There's another feature of quantum mechanics. When I go to query, when I open the door to the library to ask you, I only meet one of your selves. So they call this the measurement problem. Why is it, if all that's going on, when I look, it all goes away? If they've all talked to each other, then any one of them that I happen to come upon has the answer. And that's quantum computing in a nutshell. So here's the tricky part. What makes building quantum computers hard? I'm not doing this with humans, but we can do this with hardware in the lab now, where we can live out multiple possibilities simultaneously. They can talk to each other, collaborate on results, and the number of possibilities explodes exponentially, rather like the problems, these vast problems we want to solve. There's something called decoherence, so I'll try to describe it in a simple way. Imagine there were a couple versions of yourself. So I put you in a state of being thirsty and not thirsty simultaneously. And right now there's no reason for me to separate, so I can collaborate on some problem. But over there's a drinking fountain. I decohere. That drinking fountain interacts differently with my different selves. One goes to the drinking fountain, the other one walks the other way. I can no longer talk. I decohered, and I lose the power of that collaboration. So, elements in the environment will interact with systems in such a way to separate these paths so that they can't talk to each other anymore, and I lose the power of this quantum computation. So, what would you do? If I can eliminate elements of the environment, get rid of every fountain, every bookstore, every deli, so that I can keep those parallel strands communicating as they work on these very difficult problems, I might be able to build these magical machines. A couple of other effects you see routinely in the lab for the last 50 years. Quantum tunneling. I can have an object on one side of a barrier that will disappear, appear on the other side of the barrier without passing through that barrier. This allows you to explore regions that would otherwise be inaccessible to you. There's something called quantum entanglement. Really bothered Albert Einstein, didn't believe it. He actually showed that quantum theory predicted this, which has been confirmed again and again in laboratories all over the world. I'll tell you also a prosaic example. Imagine you had a pair of dice in London. I have a pair of dice in the US. We roll them 1,000,000 times, and I get random results. If they were quantum entangled, I fly to London, we compare our lists, and 1,000,000 rolls out of 1,000,000, they're exactly the same. With no physical interaction between these dice, they somehow are correlated perfectly across space and time. This effect now has been used to do something called quantum teleportation, wherein I have a message I want to send to a remote location. The information disappears, appears at a remote location without a signal traversing the intervening space. Guess who wants that capability? Well, it allows for perfect, secure communication. This has been done over 300 kilometers now. And this gives you an idea. Okay, if I want to build a quantum computer, I have to take some objects that have these quantum mechanical properties. So instead of bits that are either a 0 or 1, I build them out of quantum bits. Each quantum bit here, you can't see very well, I can put in a superposition of being a 0 and 1 simultaneously. Okay, so it can live out two possibilities, like on the left. If I combine that with another qubit that can be in 2 possibilities, now that combined set, I get 4 possibilities. Add another qubit, you double the number of possible paths you could explore again. And you can see that the number of possibilities explodes exponentially as you add individual units. And this is exploding in the same way as the complexity of the kind of problems I think we need to solve as a civilization. This is your own David Deutsch at Oxford, I had tea with the other day, and the way he describes quantum computing. And in a lab in the early 80s, people started getting this kind of fine control over atomic systems. So they take ions, charged atoms, they would float them in electromagnetic fields so they wouldn't touch the walls. Ultra-high vacuum, low temperatures, you're getting rid of the environmental elements that could pull the streams apart. They built a register out of this, and they were able to demonstrate all of these effects: superposition, entanglement, parallel streams of computation, combining, interfering with each other to collaborate on their answer, but only for a very limited number of qubits. Let's say you had 8, okay? You get 2 to the 8th. That's not a lot of streams, but it showed everything in principle. So this is amazing. So that one quantum register in superposition of states would equal 2 to the 8th classical registers. And you can imagine if you scale this up to, say, 300 qubits, you would have 2 to the 300th numbers contained in a single register simultaneously, which is vastly more information than there are atoms in the known universe. So this could potentially provide unimaginable computational resources. And there was an algorithm developed in 1994 by a mathematician and computer scientist, Peter Shor at Bell Labs. Brilliant guy who said, okay, there's this theoretical development that's gone on. People have seen the fundamental physical phenomenon. If I were to have such a mythical machine, he applied it to a very specific problem, factoring large numbers. So you take a number, 5, 15s, 5 times 3, that's easy. But as you make very large numbers, trying to find their prime factors, turns out the number of computations blows up, almost exponentially. So he wrote an algorithm using quantum mechanical machinations, and he showed that to factor large numbers, instead of taking billions of years on a supercomputer, you could do it in 1 second. This paper was published in 1994. It got the attention, and why is that problem interesting? Because it's at the core of something called RSA encryption, which is how people encrypt information. That needs to be very secure, and instead of taking 1 billion years to break it on a supercomputer, a quantum computer in 1 second, you can imagine how that affected all the intelligence agencies. So NSA, DARPA, all those guys started funding this robustly after that 1994 paper. Now there's lots of different ways that you could try to build a quantum computer. Most of the efforts started trying to build quantum computers out of microscopic constituents. Why? Because an electron traveling through this room right now doesn't bump into too many air molecules or photons of light, so they tend to keep their coherent evolution where these streams can maintain contact with each other for reasonable periods of time. It's very hard to engineer systems at microscopic scales. So, can you have quantum mechanics at macroscopic scales? Answer, yes. That's a D-Wave chip. There was a result in 2000 where a superconducting ring was taken to ultra-low temperatures, ultra-high vacuum, radiation shield, and we saw quantum mechanics at macroscopic scales. It was put into a superposition state of all the current going clockwise and all the current going counterclockwise simultaneously, so you could encode zeros and ones, or qubits. You can put these, this is something about how you build efforts to do this. I think I may run out of time, so I'll just get to the rest of it. We've built an organization that's rather like a MiniManhattan Project at D-Wave. We've built chips that incorporate these loops that can be in a couple of states simultaneously. We can have them interact. We have a technology that can control putting them in those superpositions, evolving them quantum mechanically, getting answers out of them. It's built something like a neural network in terms of structure. There's the chip. You have to go to rather extraordinary means to keep this from decohering. So that chip has to go into all kinds of electromagnetic shields, very complex filtering to keep the rest of the world out. It goes to ultra-low temperatures. That's something called a dilution refrigerator, where we're 20,000ths of a degree above absolute zero. That's what the box looks on the outside, some more electromagnetic shielding. It's 150 times colder than interstellar space. Magnetic field 50,000 times less than the Earth's magnetic field to eliminate these environmental couplings. And what it does is this chip produces sort of landscapes that represent very difficult optimization problems, where the answer is the lowest valley. So if you were standing in a landscape of 2 to the 500th hills and valleys, and you were behaving via classical physics, I'd start somewhere and I'd have to search that landscape. If I was a quantum system, I could span the entire landscape at one time, looking in all kinds of directions. I could tunnel through those hills, appear on the other side of mountains, and find the lowest energy state that would correspond to the best answer to a very complex optimization problem. There's 2 research centers, Google and NASA, and Lockheed Martin, forward-looking companies who have bought some of our early generations, looking at using them to search for exoplanets, to analyze very complex systems of millions of lines of codes of software and hardware interacting in complex ways, mission planning, training neural nets, pattern recognition. We've started benchmarking early prototypes. We took some off-the-shelf solvers, Cplex that underlies, sort of the Watson computer, and some stuff that they use at Google called Met's Taboo, and it works. In this case, it got answers 118,000 times faster. Now, to be fair, that was a general purpose solver. Now people have developed very powerful, specialized hardware and algorithms to try to match these early generations of D-Wave chips. We're matching that, sometimes exceeding, and so I think the point of the story is we have a processor that's harnessed these quantum dynamics. It's matching state-of-the-art that took 60 years and $1 trillion to get to, and I think we're at a tipping point. Between generations, one generation we saw a 300,000x speed up in 2 years, not a factor of 2. We've been on a Moore's Law-like trajectory where we've been doubling the number of these qubits every year. And I think the kind of unimaginable computing power that might be realized in every sector of science, in biology, industry, finance, energy, could be an astounding resource that might help me, get to the reality I dreamed about as a kid. Anyway, that's quantum computing. Thanks.
So I've got to hand it to Eric. It's a bit of a challenge explaining quantum computing in 15 minutes. And when you collect your DNA kits from 23andMe, you do collect your PhD certificate as well at the same time. So we knew this was going to be quite advanced science, and we talked about this. But we're telling the story because it's important. And D-Wave Systems is not just another startup. You've had considerable funding, for instance. How much have you raised so far?
Well, so far, $160 million.
$160 million.
Yeah, and to their credit, we have some very forward-looking venture capitalists. They're not looking for an immediate return on investment. People like Steve Jurvetson, Jeff Bezos, those kinds of people who are looking for the big end game and actually want to make a difference in the world. And it's not just about short-term profits. So.
And where are you on this journey? How far until you get the ultimate quantum computer?
Yeah, I would say that there's still significant challenges to overcome. We're kind of at this crossover point, and I think in the next few years we'll have something that will be dramatic, say the next 3 to 5 years. And then It's hard to say because there's a lot of unknown physics as you scale up these quantum systems and challenges. But I would think somewhere between the next 5 to 10 years, you could imagine quantum computers, in a cloud that scientists could access. If everything works out the way we hope it does, it's not too far away.
And this is not a government project. This is not like the original space program. This is a private company.
Yeah, it's a private company. I think that, so if you look historically at what's been going on, there was a time, in the 50s, 60s, 70s, where there were the Bell Labs of the world, right? So corporations would put money into this far-flung research. That's really not the case so much anymore. They're more risk-averse. They're looking at quarterly returns. There's some visionary corporations, of course. And then governments, haven't necessarily been stepping up in the way that they might to do this. So I see now what's happening is you have entrepreneurs, putting together really ambitious efforts. The rest of the world watches, and those corporations might acquire if. And I think it's really important. I think that this room is filled with people like that. Small entrepreneurs with big ideas. You can make huge changes in the world with the right groups of people without necessarily large government programs or corporate sponsorships.
And the final question, the ultimate challenge, I guess, is helping people here tell their friends in 140 characters or less what they've just learned.
Yeah.
So, let me start. So it's about very, very fast processes that can hold information in many forms at the same time.
Yeah, it turns out that the world we live in is a very strange place, and that physical systems can play out all the possibilities available to them simultaneously, and that those possibilities can talk to each other. And it's an extraordinary thing. There's a question is, does it mean that there's a scale of reality in which you chose a different tie today and there's a whole bunch of yous living out parallel lives? This is an open question. But whether physical systems do this is well established, this phenomenon of quantum interference where they can interact with each other. And I think that argument about is this what's really going on? As soon as a quantum computer does something that would take any conventional computer 1 billion years, that'll be the end of that. So the debate. So that's what I hope to achieve in the next few years.
We're going to have to get a quantum computer guest editing Wired one of these days. Yeah. Thank you very much, Eric Ladizinsky.
Thank you.